we're just going to demonstrate briefly the concept of strong and weak acids. Now, the common student misconception is that strong means concentrated and weak means dilute. It's not the case. Dilute and concentrated are important measures in chemistry as well, but strong and weak has a different meaning. Essentially, a strong acid is completely or almost completely dissociated in solution. So we've got a sample of hydrochloric acid. It's an example of a strong acid, and its formula is HCl. So if you had pure hydrochloric acid, pure HCl, it would have that relationship, but dissolve it in water and it's essentially all H plus ions and Cl minus ions. It's floating around as it's separate ions, it's dissociated. The other one we've got is acetic acid, or we would call it ethanoic acid these days. It's the one that's in vinegar. It is the one that can be made from alcohol with appropriate oxidization. It's why your wine will taste like vinegar if you leave it open to the air for a while. Acetic acid is an acid also, but it's a weak acid. We kind of know it's a weak acid because we put it on our salad. We don't put hydrochloric on our salad, but it's also a weak acid basically because it doesn't dissociate much. Its formula is CH3COOH, and that H at the end is the one that makes it an acid. So when it dissolves in solution, it turns into H plus ions, which is what makes it an acid, and CH3COOH ions, negative ions. So what we'll see, what we're going to do is use a pH meter to test the pH. These are both 0.1 molar solutions. So in terms of being concentrated or dilute, they're the same, but one is a strong acid and one is a weak acid. So we should observe something different when we measure the pH in terms of the extent to which it's behaving as an acid. So I've got a pH meter here. It's a Pasco one. It's connected to the Pasco data logger, which is connected by Bluetooth to our iPad. And pH electrodes are quite delicate. It's got a little glass bulb in the end here that is so thin that it's possible for ions to go through it. It's very delicate. It lives in a little bottle of 4 molar potassium chloride, and you have to keep it damp. If you let it dry out, you've basically wrecked your very expensive pH electrode. So if you have them in your school, that's some tips about how to treat them. So first up, we're going to wash our electrode to make sure that it's clean of whatever the messy person who used it last was using it for. Clean it off, and we'll pop it in the beaker, and let's do the acetic acid first to see what the pH is of this 0.1 molar solution of acetic acid. I'll get enough to cover the tip of the electrode. Give it a little bit of a stir, and we're getting a pH of 3.2 on our scale. So that is a quite acidic pH. Remember that pH will be 7 for neutral. 3.2 is reasonably acidic and behaving acidically. Let's compare that with the hydrochloric acid, which is the stronger acid. Same concentration, different type of acid. So we'll pour a similar sample, but we don't want to contaminate that with our acetic acid. So we'll take the electrode back, give it another good wash with deionized water. So we're just making sure that it's as clean as it can be. Give it a quick wipe down with a new tissue and pop it into the hydrochloric acid, and it's equilibrating down at about 1.4, 1.3, a pH of about 1.3 compared to the 3.2 of the acetic acid. So you can see that even at the same concentration, the hydrochloric acid, being a strong acid, is much more acidic. It has a much lower pH number, therefore is a much more potent acid. I'm trying to avoid the words both strong and concentrated, but it is more acidic. And in fact, after sitting for a moment, it's gone down to 1.1 pH, which is a quite low pH. So I hope that's helpful in understanding and just remembering and explaining to your students that distinction between a strong and a weak acid. There are stronger acids than HCl. hydrofluoric acid, HF, is the nastiest of acids, and never ever get it on yourself or near yourself. And there are much weaker acids than acetic as well, but they're good examples of this concept. This is basically a quick calculation for the strong and weak acids. It was a very quick video, but there is some subtlety there that I think you might appreciate when we get into the calculations. So we said that our two acids were HCl, hydrochloric acid, which dissociates in water to H plus aqueous and Cl minus aqueous. Our second acid was ethanoic acid. I think I called it acetic acid in the video. That's an old name. It's the one in vinegar, CH3COOH. And unusual to most acids, because it's an organic acid, we normally write the H in an acid at the left, but we're going to write it at the right this time. And that dissociates according to as CH3COOH, COO minus ions, aqueous, in solution, and H plus ions. So there are a number of different definitions of acids, Arrhenius or Arrhenius, Bronsted, Lowry, Lewis, etc. But one definition of an acid is that it releases protons, positive hydrogen ions, when dissolved in water. Now, one is a strong acid, HCl is a strong acid. What that effectively means is that they're both equilibriums. You see, I didn't draw an arrow, I drew a double arrow for an equilibrium. But for the HCl, because it's a strong acid, that equilibrium is strongly to the right. In other words, in solution, the great majority of it is present as the ions, not as the molecule. Only a very small amount as the molecule. Ethanoic acid, being a weak acid, is the other way around. The great majority of it in solution is as the molecule, and only a relatively small amount has dissociated to form the ions. So we can actually measure that. What we discovered was that, let me do a little bit of a table, HCl and CH3COOH. When we measured the pH of each, I should have noted that the concentration of each, I'll put it up here, concentration of the acid in both cases, so that's just the generic term, was 0.10 mole per litre, molar. So that was our concentration of both acids. So they're the same concentration, but different strengths of acid. So the pH of the HCl was 1.4. The pH of the ethanoic acid was 3.2. Doesn't seem like a huge difference. It's 1.4, 2.8, little over twice, it seems like. But remember that pH is about logarithms, powers of 10. So actually it's a more significant difference than it looks like. So just a little reminder down the bottom that the pH of something is minus logarithm to the base 10, I think I mentioned this in the video as well, of the concentration of H+. So that's the pH. You can also have the pOH or anything else. This little p operator basically means minus log to the base 10 of. And it's just a way of converting numbers that would otherwise appear as exponents, powers of 10, negative, relatively large, complicated to write, to simple numbers like 1.4 and 3.2. So it's a convenience basically for us to use. And a pH of 7 is neutral. pH of 14 is as basic as you can get. pH of 1 or 0 in some cases is as acidic as you can get. So let's, if we calculate through solving the negative the log to the base 10, and I'll actually do that down at the bottom in a moment, but let's present and compare our results first. So the concentration of H plus, square brackets for concentration, in the HCl was 0.0398 molar. Now what does that mean? We dissolved 0.1 molar, and this is about 0.04. So about 40% of it is actually dissociated in practice. Now there might be some issues with our experiment because I think it probably goes even further than that. But certainly the concentration of H plus ions is about 40% the concentration of the HCl according to our experimental data. Whereas at 3.2 for the ethanoic acid, it's 0.00063. So that's tenths, hundredths, thousandths, ten thousandths, but we were at oneths already, so it's a thousandth or so, 1,000th, sorry, of the ethanoic acid is dissociated, and the rest is cruising around as CH3COOH molecules in solution. So hopefully that is relatively clear in giving you a sense of what we mean by a strong and weak acid, and how, although the pH numbers are not very different, the concentrations are very, very different, like 2 orders of magnitude different. So just quickly going through that calculation. So if I use the, let me use the HCl because the numbers are more sensible. So if I use 1.4 equals minus log to the base 10 of the concentration of H plus, which is what we're trying to find, we'll do the same thing to both sides, which means let's get rid of the minus sign by multiplying both sides by -1. Minus 1.4 equals log. We're specifying log to the base 10 because there's also the natural logarithm to the base e that we often use. So that's why we always say that rather than just say log, lest there be confusion. And to get rid of a logarithm, what you do is raise the whole thing, raise 10 to that power. So 10 to the minus 1.4 is equal to concentration of H plus. And then we'll just flip the sides because we like the subject to be at the left, concentration of H plus, and if we calculate that, we find that gives us the 0.0398 molar. It's still a molar, it's moles of H plus ions per litre of solution.